distribution of charge, and it'll Gauss's law lets you calculate the electric field. So if you put kinks on this sheet, then you can't, that calculation becomes harder. The sheet has to be infinite and flat. Okay. Well, do we encounter, what useful is it if the sheet has to be infinite? Have you ever encountered an infinite sheet? No. But, we use capacitors, parallel plate capacitors. So here's a capacitor. Give me 2 sheets of paper. Don't have to rip it. I'll give them back to you.
This notebook's weird.
What's that?
This notebook's weird.
So why do we care for 2 infinite sheets? Here's the 2 sheets. And you can make a capacitor like this. You use 2 aluminum sheets. And these are 10 inches by 10 inches. And if they're 2 millimeters apart, the space in between, as far as you're concerned, this is an infinite sheet, right? So if you're an ant, is this sheet infinite to you? Right? So that's the idea. Okay, what is infinity? Let's say if you're an ant and you're walking to Palm Coast, how far is Palm Coast to you?
Effectively infinite.
Oh, there you go. That's the point. Yeah. You guys understand? All right. So, all right. So we will use that to calculate that. Okay. So now let's go through build up the tools for that. Okay. So let's say this is a river flowing. You have a ring like that. So this is a velocity field. This is the velocity field. What is this indicating? See, what it's telling you is that's the speed of the river at that point. Okay, and the density of lines tell you the magnitude of the field velocity, and the direction tangent to the vector is the direction of the water flow. Okay. Now you can ask the following simple question. How many gallons of water are flowing a minute through that ring? Right? That's the flow rate. That's the volume flow rate. And the volume flow rate is given by the area times the speed of the river. Okay. How much water is flowing through this ring?
0.
0. How much water is flowing through this ring?
Which one?
Which one?
This ring. What you do is,
Be like a trig function?
hmm?
Like a trig function?
It will be. So what matters is the area perpendicular to the flow. Okay? And this angle is theta, which is that angle. And so that area is A cosine theta times V. So that's the flow rate. And you saw that for this guy, the angle would have been 90 degrees, okay? And cosine 90 is 0, and the flow rate is 0. Okay. Anybody remember what is the formula, what is the value of A dot B, dot product of 2 vectors? AB cosine theta. Yeah. AB cosine theta, where A, and there's the theta. Okay, it's AB cosine theta. Okay, so this formula looks like that. Okay, exactly like this. And so, if we can define an area vector, then we can write this formula like that. Okay, we like to write things concisely. Okay, so here's how we'll define the area vector. The area vector, the direction of an area vector will be perpendicular to the area. And what do you think is the magnitude of the area vector?
The area.
The area. There you go, all right? So that's how we define the area vector, okay? So the flux, material flux, flux meaning how much water is flowing through that area per second is V dot area, okay? That tells you how many gallons of water are flowing through that ring per second, okay? And just so you know that, what are the units of velocity?
Meters per second.
Meters per second. What are the units for area?
Meters squared.
Meters squared. What are the units for cosine theta? Huh?
Radians? Or degrees?
Cosine theta, sine theta, log, huh? Exponentials. All those have no units. Okay? So this is meter cube per second. That's volume per second. Okay, that's the flow rate. All right, so now we'll remember we want to apply all of this to electric fields. So now let's consider a region where you have an electric field. Okay, so they're indicated by these, so this vector field is indicated by these lines. The density of lines telling you the magnitude of the electric field, and the direction is given by those, the direction in which the lines are pointing. So the magnitude of the electric field at a point is indicated by the field line density. Stronger the field, the density of lines is more, okay, higher. So now we'll define electric flux, just like material flux. We'll define it as E, the magnitude of the electric field, times the area, okay, when the fields are perpendicular. This just tells you, so the flux is denoted by phi, subscript E telling you we're doing electric flux. In a later chapter, we'll calculate magnetic flux. Magnetic fields are denoted by B, okay? So the electric flux is the electric field times the area. And this just tells you, like this told you what is the amount of water flowing through that thing. This tells you how many lines are threading this area, okay? So the flux tells you how many lines are threading that area. Stronger the field, more lines will go through the area. If the field is 0, how many lines are threading that area? 0. Yeah. Yeah. So that's what that tells you. Okay, so let's say if the area is at an angle to the fields, again, the area vector is pointing in this direction, and so the effective area will be A cosine theta. And so we'll define the flux just like that, E dot area. Okay, so if this area was like that, how many lines would be threading that area? 0 lines, okay? There's the area vector. All right, so now let's say there's an electric field in this room. We draw an enclosed volume, any enclosed surface. You can think of a basketball. It doesn't have to be a physical object. It can be a beach ball. It can be anything. Okay? What we want to do is calculate the flux through that area. Okay? All right, so here is an imaginary surface. I want to calculate the flux through this entire surface. So so in this room, there is the electric field, and there is the imaginary surface. Okay, we want to calculate the flux through that. Okay, let's break this up into little pieces. There is the area vector, okay, and you're always drawing, the area vector always points to the outside of the volume. Okay, that's the positive direction. And there's the electric field. So the flux through this, what is the flux? The number of lines threading that area is given by that. And what is that summation sign? You've broken it up into all little pieces and you're summing over the entire surface. And that's the flux through that surface. Okay. When do you replace summation signs by integral signs?
When
When n goes to infinity, when the pieces become smaller and smaller, then you replace the sum by an integral. Okay? And now, if this surface is an enclosed surface, if it's like a basketball, then what you do is to indicate that it's a closed surface, you put a ring around that surface. Okay? So the flux is a surface integral. Okay? It's E dot dA over a closed surface. It's a surface integral. Okay? It's a two-dimensional integral. The area will involve two coordinates. So, and here's the rule. Flux is positive when lines project outwards from the surface, and negative if they're projecting. So this is giving a positive flux, and these lines are contributing a negative flux. Okay? So that's what that is. So for a closed surface, okay, the flux is given by this surface integral. Okay? If more lines are leaving the surface than entering it, the net flux is positive. Yeah. Okay, so here's the surface. You can count the lines. If 100 lines are leaving and 90 lines are going in, the net flux is positive. Okay? If 80 lines are leaving and 120 lines are going in, then the net flux is negative. Okay, minus 40. So here's a simple calculation. Okay, so let's say in this room the field is uniform. Okay, the direction is constant and the magnitude is constant everywhere. Let's calculate the flux through a cube. Okay, so the flux through this area is just the electric field. The electric field is constant times the area of this face. And the lines are coming out, so that is positive. That's this term. The flux through this face, the area vector is pointing in this direction, the electric field is pointing in that direction, area vector is pointing in that direction, electric field is pointing in this direction. E dot area is E times area times cosine theta. Theta is 180 degrees, which is minus E times area, which is this term. The flux through this face, these four faces are 0. The net flux through that thing is 0. So for a constant electric field, the flux through this cube is 0. Now, we've oriented this cube like that, but it turns out you can orient it any way you want, and it'll still be 0. And not only that, it can be any surface. The flux in a constant field through an enclosed surface is 0. It'll come out to always be 0. Yeah, I know this is a long story, but what is the point of this? What is it that we're trying to do? We want the ability to have, we are learning a technique to allow us to calculate electric fields for symmetric charge distributions. Okay. So we want to be able to calculate the electric field for certain charge distributions. Okay. All right, so what Mr. Gauss realized was the flux through an enclosed surface, see that's an enclosed surface, the flux through an enclosed surface is related to the charge inside the surface. It's the charge inside the surface divided by epsilon naught. Epsilon naught is permittivity of free space, and that's equal to that. So here's an interesting fact. So if in this room you have a uniform electric field, and the way to create a uniform electric field is if you spray that wall evenly with positive charges and this with evenly with negative charges, you can have a you can have a uniform electric field. Okay, that's what a parallel plate capacitor does. Okay. So a parallel plate capacitor, you can have. No, I'll show you now in a second. And you use these capacitors all over the place. Okay, this will create a uniform electric field like that. Okay, so now let's go back to Gauss's law. Okay, so if the field is uniform, the flux through this is zero, that means the charge inside is zero. So if there's a uniform electric field in this room, you can you can state that there's no free charges anywhere in this room. Okay? So let me show you that uniform electric field. All right, so here's a parallel plate capacitor. And in the next chapter, you'll learn what a capacitor is. You take two pieces of metal, so you can take two pieces of aluminum foil, okay, and connect it to a battery. And what happens is electrons float from here to there. And we'll show you the electric field. There is the electric field that's uniform. Electrons float from here to there. And they repel these electrons, which move from here to there. What is a battery? What is a battery?
Something that stores energy.
It's a packet of energy. With energy, you can do stuff. Okay, you can do work. So what happened was, when electrons moved from here to there, what you did was you transferred some of the energy from here to there. That's what you did. Why did you do that? Hmm?
You can use the energy to turn on the light bulb.
Well, why did you need this fellow? Why didn't you turn it on directly from the battery?
Well, we do control the voltage
Huh?
or the amps to
Okay.
control how much energy flows through.
Okay, so if you invent a device, there's a use for it, right? Okay, so it turns out that how fast does your battery die? The battery in your flashlight, how long does it last? Hours, days, okay? If you continuously use it, it'll last several hours. So this device releases its energy slowly. A capacitor can release its energy in a billionth of a second. Okay, if you want to release it that fast. So what you've done is you transferred energy from this device to this device, because this device can release the energy fast. Okay, and see, now you release that energy through a flash bulb, and what did that flash bulb do? It turned, if this room was in utter darkness, for a millisecond, it can turn it into daylight. Okay? If this was somebody's heart that was beating chaotically, that's fibrillating, you can jumpstart reset their heart so it starts beating regularly. That's what when those guys hit you with a paddle, that's what they're doing. Okay? So we'll talk about capacitors. So anyway, the point here was, you see, in parallel plate capacitors, the electric field is uniform. And whenever you have a uniform electric field, there's no charge in that region. Okay, so you learned that, now you know that from Mr. Gauss. Okay, so the flux, this is Gauss's law. The flux through an enclosed surface is equal to the charge inside divided by epsilon naught. Okay? So for instance, through this surface, what is the total charge inside?
Zero.
Zero. So there are as many lines going in as coming out. Okay? The flux through this thing is, there's no charge inside, so the flux through that is zero. Okay? All right. We won't worry about. Okay, so what this shows you is, so this is the flux integral, and again, this is in general, this integral is not easy to do. You do it in very symmetric cases. So so let's say you have a point charge, and from a point charge, the electric field is symmetrically distributed like that. And so this integral is easy to do. Okay, so this integral would be the electric field times this area. Okay, and if you're at if this is at the center of the sphere, these electric fields are constant. So the flux would be the electric field times the area, delta area. And the integral would be just sum of that. And since the electric field is constant, sum of the areas. And what is this? What is the total area of a sphere?
The third pi r cubed.
That's the volume.
It's just
Oh.
R squared.
For area has r square, volume has r cube, distance cube, length has r. Okay? So from dimensions. Okay. And so the flux is that E times 4 pi r squared, and Mr. Gauss tells us that's equal to the charge inside divided by epsilon naught. So if you solve for E, it's Q over 4 pi epsilon naught r squared. 1 over 4 pi epsilon naught is Ke, and there's the electric field from a point charge. So that's all this is showing you. So using Gauss's law, we showed you the electric field from a point charge. Okay. So using a hammer, we killed a fly. Okay, that's what this thing was about. Okay, so what this is let's say this is a styrofoam ball, and you charge it uniformly. Okay. And what this, using Gauss's law, you can show this. What this shows you is, if the radius of the styrofoam ball is A, the electric field at the center of the ball is 0. And this is showing you the magnitude. And if the charges are positive, the electric field is always pointing out. At the surface, the electric field is maximum. And then once you go out, the strength of the electric field decreases like that. That's what this graph is telling you. Yeah. So this is for a uniform charge distribution. Yep.
Could you go back one slide? What is KE?
Ke is the Coulomb's constant. Interestingly, this graph, so if the Earth were uniform, this would be the force of gravity on you. At the center, or this is the acceleration due to gravity. At the center, the acceleration due to gravity is 0. And the acceleration due to gravity is maximum on the surface, which is what?
9.8.
Meters per second squared. And once you go further, Earth's acceleration due to gravity falls down. So this is the exact same expression. Yep.
Wait, so if you went underground, gravity gets weaker?
Yep.
Really?
Yeah, and at the center, if you find yourself at the center of the Earth, you'll be weightless. Yeah.
Has that been like proven by experiment, or is this just? That just sounds so counterintuitive. I wonder if it actually is happening.
Have you ever seen an atom? You've seen an atom.
Oh, no, that's true.
You believe in the atom.
Yeah. Oh, I see.
So do you know the radius of the Earth?
Half the diameter of the Earth. Details.
4,000 miles, 6,400 kilometers. Okay. The deepest hole we've dug is 4 miles. That's 0.1%. We'll never get to the center of the Earth. Okay.
But, and we haven't been far enough down to really see a difference.
Yeah. Well, with very sensitive instruments you can measure. Again, gravity is different in the bottom of some mines. Yep.
Do we just assume that it stays, if we're using the really sensitive equipment
Mm-hmm.
and we measure it at the bottom of a mine, do we just assume that it's the same at the center of the Earth, or have we actually?
Well, okay. This is for a uniform Earth. The Earth is not uniform and stuff like that. Okay. So in fact, if there's minerals here that has density, minerals with metal that has density higher than the surrounding thing, if we have instruments that will measure the gravity is to be different here than here. So you can detect ores like that. So it's like
I mean, I get it,
Mhm.
we don't know 100% that we would be weightless at the center of the Earth.
oh, we know 100%.
But how did we find it?
That's what the
You
math
don't
says.
have to, what?
That's what the math says. And
Mhm.
if you think about it, gravity is caused by mass, and if you're at the center, all the mass is around you, so pulling
I
out
have-
would be equal. Think of like the eye of the storm,
Does
like
that-
a hurricane.
Does that have
So-
to do with the distance you are from the center, basically?
So here is a very important theorem that Mr. Newton proved. So here's a basketball, and this was important. So a basketball, it has to be uniform density. Mr. Newton proved that if you're inside the ball, anywhere inside the ball, the force of gravity on you due to the ball is 0.
But if the Earth isn't uniform, how can we assume that being at the center, you're going to be weightless?
Well, so that the statement was if it's uniform.
Oh, okay.
And for all practical purposes, it's uniform. Okay, so now we go here. If you're inside this shell, the gravity is 0 on you. Inside this shell, it's 0 on you, and then you get to the center eventually, it's 0 on you.
It reminds me of like the angular momentum moment arm stuff. Like the force, no matter how far away, and like the angle you're pushing at. Is that related at all? Because like the max you said was on the
Surface.
right? So it's the furthest away,
Mhm.
tangential to it.
No, it's maximum because now you captured the most mass. Mhm.
If we were at the center of the Earth, would there be any gravitational effect from like the surface? Because there's mass
So
on
this
the
was the
surface.
crucial theorem. If you're inside a shell, the shell has 0 gravitational force on you. What Mr. Newton showed was this shell attracts you, and that shell
Okay.
equally balances.
Okay,
That's
so it's not that there's no gravity, it's just that everything is evenly
canceling.
Oh, okay.
Mhm. Yeah, if Austin pulls your left arm and she pulls your right arm, the net force on you is 0.
No, she's going that way. I'm not strong enough for that.
Uh, okay. All right, so okay, I'll prove one result for you showing Gauss's law. But now again, here's an infinite sheet. This is an insulating sheet, non-conducting plane. You know? So you could use a cellophane sheet, spray it evenly with charge, and now here's a side view of the sheet. Okay, so from symmetry you would assume that the electric field is pointing perpendicular to the sheet. Okay, and all these arguments go out the window as soon as there's a kink in the sheet. Okay, so it's got to be a flat sheet. And then what you would do is you would draw a Gaussian surface, a cylindrical Gaussian surface. So I'm doing the side view. Here is a more tilted perspective. Okay. So what Mr. Gauss says, the flux through this surface should equal the charge inside. Okay, the sides do not contribute any to the flux. Only this face and this face contribute to the flux. So this will be E times area plus E times area. And that should equal the charge inside, the charge on that there, divided by epsilon naught. Well, the charge is the surface charge density times the area, divided by epsilon naught. So 2EA equal to sigma area okay, so we really never do this integral except in the case of a very symmetric case. And then, you know, so the value of this integral was that. Yeah. So again, what is the neat thing about this formula? So if the sheet is infinite, you see the electric field is constant. There's no distance information. The electric field 1 millimeter from the sheet is the same as in the next galaxy. The electric field in this entire half of the universe is constant. In this entire half of the universe is constant. Infinity is a funny thing. Here's an infinitely long wire. Okay. And again, why would you do that? Because you see in this thing, if you're between these two plates that are close together, these plates might be, as for all practical purposes, are infinite. Okay? It's like that ant walking to Palm Coast. You know? All right, so let's do this. An infinitely long wire, the charge is uniformly distributed, and lambda is the linear charge density. What does that mean? That's the charge per unit length. Okay, and again, so if there's the electric field has to be symmetric at a given distance. It'll have, and it's perpendicular to this surface. Okay, so we'll calculate the electric flux through this surface. So we are doing this integral, but not really doing it. Okay. What is the contribution to this integral of this phase? 0. Of this phase? 0. There's only contribution of this phase. It's E times the area of this phase. What is the area of that face?
Circumference times height.
Very good. Very good. Circumference times height. 2 pi r times L. And that is equal to the charge inside, and the charge inside is just lambda times L divided by epsilon naught. So E is lambda divided by 2 pi epsilon naught r. But Ke, the Coulomb's constant, is 1 over 4 pi epsilon naught. So we'll multiply that by 2 and divide by 2, and that becomes 2 Ke lambda by r. So that's the electric field. All right, that's so. Remember, we started off by shaking our heads on the prospect of finding the electric field everywhere in this room, because it was a matter of adding a whole bunch of vectors. And now the class is over. Should we give her attendance grade? Let's take a vote.
Well, we didn't even make a sheet yet, I don't think, so.
Oh,
start it, don't worry.
no, he's on your side. He's on your side, and I'm disappointed in him. All right, so for an infinitely long wire, we've calculated the electric field. Okay. All right, so here are some interesting applications. You guys know how your cell phone doesn't work in certain buildings? Okay, so we'll find out why.
Fair-
I'm sorry?
Like a Faraday cage?
Yeah, it's a Faraday cage. And we'll find out what a Faraday cage is. Okay, it turns out that, so let's say this is a piece of metal. Okay, and so you smear that wall with positive charge, negative charges. In this room, you'll have a uniform electric field. And now you walk in with a piece of metal like this. Here's what will happen. Okay, in a metal, there's plenty of free charges, and electrons will collect on this face, and this face will become positive. So here's the external field, and these guys will produce a field themselves, and this field will cancel that field inside. And the net field inside the metal will be 0. So these charges will redistribute such that the field inside the metal is 0. And this happens almost instantaneously. It'll happen in about 10 to the minus 18 seconds. You can't even blink your eye that fast. So if you have an electric field, again, constant electric field, so it can change slowly if it wants. It can slowly compared to that time, which is even your cell phone signal. Okay? You bring this metal, the electric field inside the metal, the charges redistribute such that the electric field inside goes to 0 instantly. How strong a field do you need to create lightning?
3 times 10 to the 6.
I'm sorry?
3 times 10 to the 6.
3 million volt per meter. Never ever forget this number. Okay? All right, so now let's do the following. So here's a metal box, a shipping container if you want. Let's flip a switch, and the electric field outside here is 4 times 10 to the 6 volt per meter. So that's not good for your health. Soon as you switch this, but what will happen? Electrons will collect over here. This end will become positive. in this entire region, this electric field is canceling that electric field. So in this entire region, the electric field is 0, inside the box and within the metal. These fellows here are in lightning, sitting in lightning. There's lightning happening all over. There's nothing. Electric field here is 0. You're perfectly safe. So in a lightning storm, one of the safe places is a car if it's made out of metal. If this is a cell phone signal, again, the cell phone signals are gigahertz, 10 to the 12, okay, 10 to the minus 12 seconds. No, 10 to the minus 9 seconds. Stuff is changing over 10 to the minus 9 seconds. But remember, this stuff happens within 10 to the minus 18 seconds. Yeah. So cell phone signal doesn't penetrate a building with a lot of metal. So if you want to shield the inside space from outside electrical fields, you just have lots of metal. Yep. So you go into a chicken coop. We can do this experiment. It's easy to do. Have your friend call on your cell phone. The signal won't get through.
Does the outside electric field still penetrate it, but it's just canceled by the inside electric field?
Yeah, you can say it like that. Yeah. Mm-hmm. Mm-hmm. So, here, see, the field is strong enough to have lightning outside, and inside it's perfectly safe. I got to experience this. All right, so in electrostatics, what happens is, here's the driving phenomenon. The charges redistribute such that the electric field has to be 0 inside a metal. Okay? So the charges will redistribute such that the field inside that's the goal, to make the field inside a metal 0. If it's not 0, then there are free charges, they'll move about so till the field becomes 0. So no matter what you do. So let's say you throw a bunch of charges here. What you'll find is, since the field inside has to be 0, you can draw any surface. The charge inside has to be 0. So if you throw a bunch of extra charges, they all have to reside on the outer surface. And since the field here is 0, they cannot reside on the inner surface. They all have to be on the outer surface. Okay? So that's how the charges will redistribute. So anything you're answering, it's what you're saying is, stuff happens such that the field inside a metal has to be 0. This is in a static situation. Now, in a couple of chapters, you'll learn when here's a piece of metal, that is a wire, you connect a battery, this is a dynamic situation. And what this guy does is, he establishes an electric field inside the metal. Okay? And that is what drives the current. Okay? And so electrons move in this direction. So this is different than this. So here is a Faraday's cage. So if you had a metal ball and you put a charge there, what needs to happen?
Electric field goes to 0 inside.
You have to do things need to happen so that the electric field here is 0 inside the metal. And here's how it'll happen. Okay, so here's a negative charge, and positive charges will you'll have positive charges on the inner surface of this metal and negative charge here. And here's very interesting. Can anybody guess at how these positive charges are distributed? $1 for head. Anybody who does.
Evenly?
No.
Not evenly. That's the best guess so far.
It was very good, yes. Okay, so they distribute such that the center of this positive charge is right on top there. That way, the electric field of a negative charge, which is this coming this way, is being canceled by the positive, the field of this positive charge. All right, so again, you can think about that. So the this was a -1 unit charge. This will be a total of +1 unit charge, and it's redistributed that its center of mass or center of gravity is right there. And then there'll be a 1 unit of negative charge because these electrons float over there. And these guys are evenly distributed. So here's a puzzle. If you had a metal sphere and you have a charge inside, you will see an electric field outside, except that the field is uniform. And so from looking at this field, you don't know where the charge is located. The charge can be located anywhere. So the metal shield shields your view. Metal sphere shields your view of the charge. You don't know where the charge is. Okay. All right, here's a metal, here's a conductor. You put a bunch of charges on here. And what would the charges want to do? Let's say you put a bunch of protons. Of course, they repel each other, so they want to be as far as possible. But when you come to sharp edges, there's no room to run away to. And so near sharp corners, the charge density is higher. Here, the charge density is lower. Okay, so from an insulating sheet, you see the electric field can go either way, and so the electric field is sigma by 2 epsilon naught. From a metal surface, it can only go outwards. The field inside is 0. So the field just on the surface is sigma by epsilon naught. Okay, sigma by epsilon naught. Okay, so what does this expression tell you? How do you get the field to be larger? Where is the field the strongest? Wherever the density is the highest. Epsilon naught is a constant, you can't change that. This, wherever the density is highest. Okay, so let's come to this metal. The density is lowest here, the field is weakest here. The density, surface density is highest here, the field is highest here. So here is a sharp piece of metal. This is showing you that the electric field is the sharpest. What do you need to create lightning?
A lot of charge.
3 million, electric field of 3 million volts per meter. So, if you had a bunch of charges, where is it likely that lightning will strike? Here. That's where the electric field is the strongest. Okay. So that's why one of your most expensive investment is a room with a roof, and so they always put a lightning rod on it. Yeah. So instead of hitting there, lightning will be conducted through this wire, and the charge, excess charge, will be sent to the ground. Yeah. All right, I'll tell you one thing. I won't go through the proof, but here's an interesting mathematical fact you want to know. Okay, so here's a circle. Here's the radius. Here's an angle. Here's the arc length. Okay, S divided by R is theta. And what are the units for this angle? This is in radians. Okay, so when S is equal to R, that is 1 radian. and that angle is about 60 degrees, it's 57 and change. Okay? So this is for a circle. Let's generalize it to a basketball. Okay? Now, for a basketball, instead of an arc length, what does it become? It becomes an area. And instead of an angle, it becomes a solid angle. It becomes a cone. Okay? So for a basketball, you have an area. Okay? And area divided by r squared. So now you want to make that number dimensionless. So the area, so here's the area cosine theta, here's that area cosine theta. This is the relevant area. That area divided by r squared. And that angle is called a solid angle. It's denoted by omega. Okay? And it's called a steradian, just a generalization of that. And of course, you can keep going. So this is a two-dimensional sphere embedded in 3 dimensions. You can embed a 3-dimensional sphere in 4 dimensions, a 4-dimensional sphere in 5 dimensions, and so on. Okay, and you can generalize that. So that's the solid angle, and the totals. What is the total angle here in the circle? How many radians? 2 pi radians. For a solid angle, it's 4 pi steradians. Okay? So that's generalization of the angles.